There is a silence in the deep void that the human mind is not evolved to comprehend. It is not merely the absence of sound, but the absence of anything against which to measure your own existence. In this crushing stillness, distance becomes a monster that devours time. If you were to look out the window of a spacecraft traveling at the speed of a commercial airliner, cruising comfortably at 600 miles per hour toward the nearest star, you would die of old age before you had even left the gravitational shadow of our own solar system. Your children would die. Their children would die. Generations would rise and turn to dust. Civilizations would be built and forgotten, and your ship would still be floating in the dark, barely having moved a single inch on the cosmic scale. This is the terrifying reality of the universe we inhabit. It is a reality defined by a single, suffocating paradox. We have mastered the art of moving fast, yet we remain almost perfectly motionless. To understand the true limits of human exploration, we must first confront the machinery we have built to fight this distance, and realize why even our most violent record-breaking speeds are nothing more than a crawl in the dark. At this very moment, diving through the superheated corona of our star, lies the current champion of human velocity. The Parker Solar Probe is not just a machine, it is a defiant scream against the laws of thermodynamics. As it falls toward the sun, surrendering to the terrifying grip of solar gravity, it achieves speeds that seem hallucinated rather than calculated. It is currently tearing through the inner solar system at over 430,000 miles per hour. Let us pause to truly visualize that number, because the human brain is bad at processing such scales. At 430,000 miles per hour, you are moving fast enough to travel from New York to Tokyo in less than 60 seconds. You could circle the Earth's equator 17 times in the span of a single hour. If a rifle bullet were fired next to this spacecraft, the probe would leave the bullet behind as if it were standing still in mid-air. The kinetic energy involved is so immense that a collision with a grain of sand at this velocity would deliver the explosive force of a grenade. This spacecraft represents the absolute apex of our species' engineering capability, the result of centuries of mathematical refinement, billions of dollars in investment, and the collective genius of thousands of scientists. And yet, this miracle of engineering, this fastest object ever touched by human hands, reveals a devastating truth. If the Parker Solar Probe were to turn away from the sun and maintain this record-breaking velocity in a straight line toward Proxima Centauri, our nearest stellar neighbor, the journey would not take days. It would not take months. It would not even take decades. Traveling at a speed that would vaporize flesh instantly, the probe would require nearly 7,000 years to reach the next star. 7,000 years. To put that in perspective, 7,000 years ago, human beings were just beginning to experiment with copper tools. Writing had not yet been invented. The woolly mammoth was still walking the earth on remote islands. If you had launched this mission at the dawn of recorded human history, it would only now be arriving at its destination. This is the velocity trap. The universe has built a cage around us, not made of walls, but made of sheer, empty distance. The gap between what we perceive as fast and what the cosmos demands is so vast that it renders our greatest achievements statistically irrelevant. To achieve even this insufficient speed, the Parker Solar Probe has to cheat. It does not carry an engine powerful enough to drive it to 430,000 miles per hour. No such engine exists. Instead, the probe performs a high-stakes gravitational ballet, a dance with the planets that physicists call a gravity assist. The concept is elegant and slightly parasitic. By flying dangerously close to Venus, the spacecraft dips into the planet's gravity well. As it swings around the planet, it effectively steals a tiny fraction of Venus's orbital momentum. Venus slows down in its orbit around the Sun by an amount so small it is unmeasurable, while the tiny spacecraft gains a massive boost in velocity. It is a cosmic theft, robbing a planet of its energy to fling ourselves faster into the fire. The probe repeats this maneuver, looping over and over, tightening its orbit, falling faster and faster toward the Sun. It endures heat exceeding 2,500 degrees Fahrenheit, relying on a carbon composite shield just 4.5 inches thick to keep its instruments from melting into slag. We are pushing the absolute limits of material science just to achieve a speed that is still, cosmically speaking, a standstill. The tragedy of our situation becomes clearer when we look backward at the history of human motion. For the vast majority of our existence as a species spanning nearly 200 millennia, the speed limit of humanity was biological. We could move as fast as we could run, or eventually as fast as a horse could gallop. For thousands of years, the world was measured in days of travel, not hours. The horizon was a hard limit. Then, in a sudden explosion of progress that spanned less than a single century, we broke every barrier. We went from the steam engine to the internal combustion engine, from the propeller to the jet turbine, and finally to the chemical rocket. In 1969, the Apollo astronauts returned from the moon at speeds approaching 25,000 miles per hour. It felt like we had conquered velocity. We looked at that exponential curve and assumed it would continue upward, that by the year 2000 we would be cruising to Jupiter. But we were wrong. The curve flattened. The Parker Solar Probe is faster than Apollo, yes, 17 times faster. But 17 times a crawl is still a crawl when the destination is light, years away. We hit a wall, unseen but impenetrable, dictated by the chemistry of combustion and the tyranny of the rocket equation. Consider the Voyager 1 spacecraft to understand the profound loneliness of this limitation. Launched in 1977, Voyager 1 is the most distant human-made object in existence. It carries a golden record, a phonograph disc plated in gold, containing the sounds of earth whales singing, thunder crashing, a mother kissing a child. Greetings in 55 languages. It was intended as a message to the stars, a bottle cast into the cosmic ocean. But the ocean is far wider than its creators could have emotionally comprehended. Voyager 1 has been traveling for 47 years. It has never stopped. It has never slowed down. It flies through the dark at 38,000 miles per hour. And after half a century of constant, unrelenting flight, it has covered approximately 15 billion miles. To a human mind, 15 billion miles is an abstraction, a number too big to feel. But let us shrink the universe to a human scale. If the distance between the Sun and Proxima Centauri were scaled down to the distance between New York City and Los Angeles, a journey of roughly 2,800 miles, then Voyager 1 after 7 years of maximum effort has traveled about 100 feet. It has not even left the driveway. It is still visible from the front porch. In 2012, Voyager 1 officially crossed the heliopause. This is the magnetic boundary where the solar wind, the stream of charged particles flowing from our Sun, finally loses its strength against the pressure of the interstellar medium. The scientific community celebrated humanity had left the solar system. But this is a technicality of magnetism, not gravity. Gravitationally, Voyager is still firmly in the suburbs of the Sun. It has not yet reached the Oort cloud, the vast shell of icy debris that marks the true edge of our star's dominance. It will not reach the inner edge of the Oort cloud for another 300 years. It will not pass through the cloud and truly escape into the galactic void for another 30,000 years. 30,000 years. By the time this primitive machine truly leaves our solar system, the civilization that launched it will likely be long gone. The golden record will be playing to no one, a silent disk of gold drifting in the cold, carrying the voices of ghosts. The probe's nuclear heart, a generator powered by the radioactive decay of plutonium-238, is slowly dying. It loses 4 watts of power every year. By 2025, Mission Control will have to start shutting off its last scientific instruments to save power. By the mid-2030s, Voyager will go silent forever. It will become a dead artifact, tumbling through the darkness for eternity, never reaching a star, never being found, simply a piece of space junk marking the spot where a species tried to leave its home and failed. The barrier that traps us here is not a lack of ambition. It is a fundamental law of physics known as the Tsiolkovsky rocket equation. This equation is the gatekeeper of the cosmos, and it is merciless. It dictates the relationship between a rocket's speed, its fuel, and its mass. The principle is simple. To move forward, you must throw mass backward. In a chemical rocket, this mass is hot gas produced by burning fuel. But here is the catch: the fuel itself has mass. To carry more fuel, you need a bigger tank and a bigger structure, which adds more mass. To lift that extra mass, you need even more fuel. And to lift that fuel, you need yet more. It is a vicious, exponential cycle. The more you try to accelerate, the harder the universe pushes back. Chemical rockets are limited by the energy stored in the chemical bonds of their propellant. When hydrogen and oxygen react, they release a specific, finite amount of energy. You cannot get more out of it than nature put in. This limits the speed at which the exhaust gas can leave the nozzle. And because the exhaust speed is limited, the top speed of the rocket is limited. To illustrate the absurdity of using chemical rockets for interstellar travel, let us look at the math. Suppose you wanted to send a small probe to the nearest star and you wanted it to get there in a reasonable time, say 50 years. This would require traveling at a significant fraction of the speed of light. To accelerate a payload of just a few thousand pounds to 1% of the speed of light using the most efficient chemical rocket fuel we possess, the amount of fuel required would exceed the mass of the entire observable universe. Not the mass of the Earth, not the mass of the Sun, the mass of every star, every galaxy, every nebula, and every black hole in the cosmos combined. The math implies that chemical propulsion is a dead end. It is a technology for island hopping, good for getting to the moon, passable for getting to Mars, but utterly useless for crossing the ocean of night. We are like a civilization trying to cross the Atlantic Ocean in a canoe. We can paddle harder, we can build sleeker canoes, but we will never reach the other side before we starve. And yet we look at the speed of light with envy. Light travels at 186,000 miles per second. In the beat of a human heart, light can circle the world 7 times. It takes light just over 1 second to reach the moon. It takes light 4 hours to reach Pluto. It takes light 4 years to reach the nearest star. Compare this to Voyager. In 47 years, Voyager has traveled a distance that light covers in less than 1 single day. We are frozen in place. The universe is vast, not just in space, but in the time required to traverse it. The distances are so great that looking at the stars is literally looking into the past. The light hitting your eyes tonight left those stars years, centuries, or millennia ago. We are trapped in a bubble of causality, separated from the rest of the galaxy by a chasm of time that our current engines cannot bridge. This realization led many scientists in the 20th century to a grim conclusion. Perhaps interstellar travel is simply impossible. Perhaps the universe is designed to quarantine intelligent species on their homeworlds. Maybe the distances are a safety mechanism ensuring that no civilization can ever spread far enough to threaten the structure of the galaxy. But this despair ignores a hidden truth, a secret written into the fabric of reality that was discovered in a patent office in Switzerland more than a century ago. The universe is not a rigid box. Space is not static. Time is not a constant river flowing at the same speed for everyone. There is a loophole, a mechanism that allows for the bending of these rules. It suggests that the barrier of distance is not absolute, and that the 80-year limit of a human life is not as fixed as it seems. The speed of light is not just a limit, it is a transformative threshold. As you approach it, reality itself begins to warp. Clocks tick differently, lengths contract. The universe plays a trick on the traveler, a trick that might just allow us to escape our prison. But to understand how far a human can actually travel in one lifetime, we have to leave the world of chemical rockets and intuitive physics behind. We have to enter a realm where speed creates time, where the faster you go, the younger you stay. We have to understand that the velocity trap we are currently in is not a permanent state, but a technological plateau waiting to be shattered. The silence of the void is not a sign that we cannot pass, it is a challenge. And the answer to that challenge lies in the strange, bending, twisting nature of space-time itself. To understand why we are trapped, we must travel back in time, not to a high-tech laboratory or a sprawling launch complex, but to a small, drafty log cabin in the Russian countryside at the turn of the 20th century. Here, a nearly deaf schoolteacher named Konstantin Tsiolkovsky sat by candlelight, dreaming of gravity. He was a man isolated by his disability and his geography, yet his mind roamed freely across the cosmos. In 1903, the same year the Wright brothers flew their fragile glider over the sands of Kitty Hawk, Tsiolkovsky published a derivation that would become the foundation of all spaceflight. It was a simple mathematical equation, elegant in its construction, yet devastating in its implications. It is known today as the Tsiolkovsky rocket equation. For over a century, this single line of mathematics has served as both our ticket to the heavens and the prison warden keeping us from the stars. It is the tyranny of chemistry codified in ink. The equation governs the fundamental relationship between a rocket's change in velocity, its exhaust velocity, and the ratio of its initial mass to its final mass. It reveals a brutal exponential truth: to go faster, you must burn fuel. But that fuel has weight. Therefore, you must carry more fuel just to lift the fuel you intend to burn later. The curve of this equation is not linear. It is a steep, unforgiving wall. If you want to double your speed, you do not simply double your fuel. You might need to triple or quadruple it. If you want to increase your speed by a factor of 10, you might need 1,000 times more fuel. The mathematics demand a payment in mass that quickly exceeds the resources of the planet. This is not a technological hurdle that can be cleared with smarter software or better alloys. It is a fundamental constraint of the universe, as absolute as gravity itself. As long as we rely on pushing matter out the back of a ship to move forward, we are slaves to this exponential curve. The root of this slavery lies in the nature of combustion itself. When we launch a rocket like the Saturn V or the Space Launch System, we are witnessing a chemical reaction on a massive scale. We take a fuel, typically refined kerosene or liquid hydrogen, and an oxidizer, usually liquid oxygen, and we force them together in a combustion chamber. At the molecular level, this is a violent dance of breaking and forming bonds. The chemical bonds holding the hydrogen atoms together are snapped, and new bonds with oxygen are formed. This reconfiguration releases energy in the form of heat, causing the resulting gas molecules to vibrate and move with intense speed. We then channel this superheated high-pressure gas through a nozzle, forcing it to expand and accelerate in a single direction. The result is thrust. It is a glorious, thunderous process that shakes the ground and lights up the sky. But it is inherently limited. The limitation is found in the speed of the exhaust particles. Even in the most efficient chemical engines humanity has ever built, such as the main engines of the space shuttle, The gas molecules exit the nozzle at a maximum speed of roughly 4.5 kilometers per second. This is the exhaust velocity, the critical variable in Tsiolkovsky's equation. 4.5 kilometers per second is incredibly fast by terrestrial standards. It is 10 times the speed of a bullet, but compared to the cosmic scale, it is pathetic. To reach the stars, we need to travel at tens of thousands of kilometers per second. We are trying to achieve relativistic speeds by throwing molecules backward at the speed of a campfire's smoke. The disparity is too great. No matter how big you build the rocket, no matter how much fuel you pack into the stages, you cannot force the chemistry to yield more energy than the bonds themselves contain. You are hitting the thermodynamic ceiling of electron exchange. This brings us back to the crushing reality of the mass ratio. Because our exhaust velocity is so low, the rocket equation demands that for any significant interstellar journey, the spacecraft must be almost entirely made of fuel. The payload, the ship, the crew, the life support systems, the scientific instruments must be a microscopic fraction of the total launch mass. To accelerate a single human being to just 10% of the speed of light using chemical rockets would require a vessel larger than the solar system filled entirely with liquid hydrogen. This is why, despite decades of advancement, our rockets look essentially the same as they did in the 1960s. They are giant towers of fuel with a tiny capsule perched on top. We are not exploring the galaxy, we are barely managing to toss pebbles across the river. The fire that allowed us to conquer the Earth and reach the moon is the very thing anchoring us to the sun. It is a propulsion system for a planetary species, not an interstellar one. If fire cannot take us to the stars, we must look for other ways to move. We must look for engines that do not roar, but whisper. Deep in the vacuum of space, a different kind of propulsion has been quietly proving itself, one that abandons the violence of explosion for the efficiency of electricity. This is the ion drive. If a chemical rocket is a scream, an ion engine is a breath. The principle is fundamentally different. Instead of burning fuel to create heat, an ion thruster uses electricity, generated by solar panels or a nuclear battery, to strip electrons from a gas, usually xenon. This creates positively charged ions. The engine then uses a magnetic or electrostatic field to accelerate these ions out the back of the spacecraft at tremendous speeds. The exhaust velocity of an ion engine is its superpower. While chemical rockets struggle to reach 5 kilometers per second, an ion thruster can easily propel particles at 40, 50, or even 90 kilometers per second. This 10-fold increase in efficiency completely transforms the rocket equation. It means you can get much more velocity for every ounce of fuel you carry. You do not need a tank the size of a universe. You can carry a modest supply of xenon gas and still achieve impressive changes in speed. But there is a catch. There is always a catch. While the exhaust velocity is high, the total amount of matter being expelled is tiny. The thrust produced by a typical ion engine is roughly equivalent to the weight of a single sheet of paper resting on your hand. Imagine trying to push a car with the force of a sheet of paper. At first, nothing happens. The car does not move. But in the frictionless environment of space, there is no resistance. If you keep pushing with that tiny force, second after second, hour after hour, day after day, the spacecraft will eventually begin to drift. Then it will glide. Then it will race. The Dawn spacecraft, launched by NASA in 2007, used ion engines to explore the asteroid belt. It did not blast off with a surge of G-force. It spiraled slowly outward, its engines glowing with an eerie, ghostly blue light, the signature color of ionized xenon. Dawn accelerated continuously for years. It became the first spacecraft to orbit two different extraterrestrial bodies, Vesta and Ceres, maneuvering with a grace and efficiency that chemical rockets could never match. but the acceleration was agonizingly slow. It took days to achieve what a chemical rocket does in seconds. For a robotic probe with infinite patience, this is acceptable. For a human crew with a finite lifespan, it is a death sentence of boredom. An ion drive could theoretically take us to the stars, but the journey would be measured in millennia. It solves the fuel problem, but it fails the time problem. There is, however, a propulsion concept that discards the idea of fuel altogether. It is the most romantic and poetic of all interstellar dreams, the solar sail. For centuries, astronomers observed that comets' tails always pointed away from the sun, regardless of which way the comet was moving. They realized that sunlight itself exerts pressure. Photons, the particles of light, have no mass, but they do have momentum. When a photon strikes a reflective surface and bounces off, it transfers a tiny amount of that momentum to the surface. It is a microscopic push. But the sun emits septillions of photons every second. If you could unfurl a sail large enough and light enough, you could catch this wind of light and sail through the void just as galleons once sailed the oceans of Earth. In 2010, the Japanese space agency JAXA proved this was not just a dream with the Icaros mission. In the deep silence of interplanetary space, the small spacecraft spun itself up, using centrifugal force to unfurl a square membrane of polyimide resin diagonally across a span of 14 meters. The sail was thinner than a human hair, shimmering like gold in the unfiltered sunlight. As the photons from our sun struck the sail, Icaros began to accelerate. No engine, no fuel, no vibration. Just the relentless, silent pressure of light itself pushing the machine forward. It was a triumph of concept. It proved that we can navigate the cosmos using nothing but the energy that is already there. The beauty of the solar sail is that it never runs out of propellant. As long as there is a star to shine on it, it can keep accelerating. It breaks the tyranny of the rocket equation by removing the mass of the fuel from the calculation entirely. But the solar sail faces a different tyrant, the inverse square law. As you sail away from the sun, the light becomes dimmer. The stream of photons spreads out, becoming less dense. If you double your distance from the sun, the solar pressure drops to 1/4 of its strength. By the time you reach the orbit of Jupiter, the sun is just a bright star and its push is feeble. By the time you reach the edge of the solar system, the wind has died completely. You are becalmed in the dark, drifting with whatever speed you manage to build up closer to home. To reach another star using only the light of our own sun would take thousands of years, leaving the crew stranded in the deep cold between the stars, waiting for a destination that remains forever beyond the horizon. These technologies, chemical rockets, ion drives, solar sails, represent the current arsenal of humanity. They are brilliant, ingenious, and utterly insufficient. They are the tools of a toddler learning to crawl, while the universe demands that we run a marathon. We are trying to cross the Pacific Ocean, and we have built a very excellent raft. We have learned to catch the breeze, and we have learned to paddle efficiently. But the ocean is vast, and the supplies are low. To truly cross the void, to span the distance between the Sun and Proxima Centauri in a human lifetime, we need to abandon these gentle methods. We need power. We need violence controlled on a microscopic scale. We need to tap into the fundamental binding energy of matter itself. We must look at what happens when we stop rearranging electrons and start splitting the atom. The energy density of nuclear reactions is millions of times greater than chemical reactions. A handful of uranium contains enough potential energy to power a city or to push a ship to speeds we can scarcely imagine. This brings us to the dreams of the atomic age, when humanity briefly flirted with the idea of riding nuclear fire to the stars. It was a time when fear and ambition mixed to create concepts so audacious they border on madness. The most famous of these was Project Orion. In the late 1950s, a group of physicists at General Atomics, including the visionary Freeman Dyson, asked a question that sounds like the setup to a dark joke. What if we propelled a spaceship by detonating nuclear bombs behind it? This was not a fringe theory, it was a serious government-funded program. The design called for a massive spacecraft, built like a battleship, with a thick steel pusher plate mounted on the rear, attached to the main hull by giant shock absorbers. The ship would eject a small, directional nuclear explosive, essentially a shaped atomic bomb, out the back. The bomb would detonate, creating a rapidly expanding cloud of plasma. This plasma would slam into the pusher plate, kicking the ship forward. Then, another bomb would be ejected, and another. Bang, bang, bang. A heartbeat of nuclear fire driving the vessel faster and faster. The calculations for Project Orion were shocking. Unlike chemical rockets, which struggle to lift their own weight, an Orion ship would be incredibly powerful. It could lift thousands of tons of payload. It could carry a crew of hundreds. It could reach Saturn in months, not years. And theoretically, it could reach roughly 5 to 10% of the speed of light. At that speed, the journey to Proxima Centauri would take decades, perhaps 40 or 50 years. A single human lifetime. It was the first time the math actually worked. The physics allowed it. We had the bombs. We had the steel. We had the shock absorbers. We could have built it in 1965, but we didn't. The very idea of launching a ship loaded with thousands of nuclear warheads was terrifying. The fallout from the launch alone would have poisoned the atmosphere. The risk of an accident during ascent was a nightmare scenario. And then came the Nuclear Test Ban Treaty of 1963, which forbade nuclear detonations in space. Project Orion was killed, not by physics, but by politics and sanity. The blueprints were archived, the team disbanded, and the dream of riding shockwaves to Alpha Centauri was locked away in a vault. We chose safety over speed. We chose the clean, slow drift of chemical rockets over the dirty, brutish power of the atom. Yet the ghost of Orion lingers. It reminds us that the energy exists. The universe has locked the speed of light behind a high paywall, but the currency to pay it is available if we are willing to pay the price. Nuclear fission, the splitting of atoms, is just the first step. Beyond fission lies fusion, the power of the sun itself, and beyond fusion lies the ultimate energy source, the holy grail of propulsion, where matter and antimatter collide to unleash pure energy. These are the technologies that could finally shatter the velocity trap. But to master them, we must first understand the demons that guard them. We must understand why fusion is so hard to bottle, and why antimatter is the most expensive substance in existence. We are standing on the shore of the cosmic ocean holding a map that says, "Here be dragons," and we are deciding whether to build a ship that can survive the fire. The transition from chemical to nuclear is not just an upgrade, it is a metamorphosis. It requires us to stop thinking of fuel as something you burn and start thinking of mass as something you convert. Einstein's most famous equation, EMC squared, whispers, "The secret mass is just concentrated energy." A lot of energy. If we can unlock it, the rocket equation changes its tune. The tyranny of chemistry fades, replaced by the tyranny of heat and radiation. The challenges shift from how do we carry enough fuel to how do we keep the engine from melting the ship, and how do we keep the crew from dying of cancer. As we look at the stars tonight, remember that the silence between them is not empty space. It is a barrier of time and energy. Our current engines are merely scratching the surface of this barrier. The ion drives of the Dawn spacecraft and the solar sails of Icaros are beautiful, elegant steps. But they are the steps of a child. To become a galactic species, we must grow up. We must learn to wield fire that burns hotter than the surface of the sun. We must be willing to harness the forces that destroy cities and turn them into the wind that fills our sails. The path to the stars is paved with the shattered nuclei of atoms, and the journey has barely begun. The chemical age is ending, and the atomic age of spaceflight waits in the wings, promising speed, danger, and the only realistic hope of crossing the great dark in a single human heartbeat. If the story of space travel ended with chemical rockets and the tyranny of mass, humanity would be destined to die in the crib. We would be a species forever looking at the stars through glass, trapped by the immense suffocating silence of the void, prisoners of a geometry that prohibits escape. But the universe is not as rigid as our intuition suggests. It is not a fixed stage of absolute time and absolute distance, where a mile is always a mile and a second is always a second. Hidden beneath the surface of reality, woven into the very fabric of space and time, there is a loophole. It is a secret door that opens only when you move with sufficient violence. This loophole suggests that the 80-year limit of a human life is not a fixed boundary but a variable that can be stretched, twisted, and manipulated. To understand how a human being could cross the galaxy in a single lifetime, we must abandon the common sense of Isaac Newton and enter the strange, fluid world of Albert Einstein. The key to this door was forged in 1905, not in a high-tech laboratory, but in the mind of a 26-year-old patent clerk working in Bern, Switzerland. Einstein was a man obsessed with light. He asked himself a question that seems simple, almost childlike. What would happen if you could chase a beam of light? If you could move at 186,000 miles per second, would the light wave appear frozen beside you, like a wave in a pond that has been paused? For centuries, physics suggested the answer should be yes. But Einstein realized that this broke the fundamental laws of electromagnetism. He concluded that the speed of light is a cosmic constant. It is the absolute speed limit of the universe, and it is invariant. No matter how fast you move, light always moves away from you at exactly the same speed. This single realization shattered the foundation of reality. If the speed of light must remain constant for all observers, then something else must give way. That something is time itself. Einstein revealed that time is not a universal clock ticking in the background of the universe. It is a local phenomenon, inextricably linked to motion. The faster you move through space, the slower you move through time. This is not a mechanical error or a trick of perception. It is a fundamental property of the cosmos known as time dilation. It means that a clock on a moving spaceship literally ticks slower than a clock left behind on Earth. The biological processes of the astronauts, their heartbeats, their cell division, their aging, slow down relative to the universe they are passing through. At everyday speeds, this effect is invisible. When you drive your car or fly in a jet, time dilation is occurring, but it is measured in nanoseconds, far too small to be noticed by human senses. But as you approach the speed of light, the effect ceases to be a curiosity and becomes the dominant force of your existence. The relationship is governed by a number that physicists call the gamma factor. This number represents the exchange rate between your time and the universe's time. At rest, gamma is 1. Your time and Earth's time are perfectly synchronized. At 50% of the speed of light, gamma climbs slightly. Time aboard the ship slows down by about 15%, significant but not transformative. The magic begins when you push the speedometer toward the edge of the possible. At 90% of the speed of light, the gamma factor jumps to over 2. For every hour that passes on the ship, more than 2 hours pass on Earth. You are now living at half the rate of the rest of the world. But this is just the beginning. The curve is exponential. At 99% of the speed of light, gamma reaches 7. 7 years pass on Earth for every single year you experience. You could travel to a star 7 light-years away, a journey that light itself takes 7 years to complete. But your onboard clock would only register 1 year. You would age 1 year. You would eat 1 year's worth of food. Your mind would record 1 year of memories. But when you arrived, you would find that the universe had aged 7 years. You have effectively compressed distance by slowing down time. Push harder. Push the engines to their theoretical breaking point. At 99.9% of the speed of light, gamma exceeds 22. A journey of 22 light-years. Crossing a vast section of our stellar neighborhood would feel like a single year to the traveler. At 99.999%, gamma soars to 223. You could cross the entire galaxy, a disk of stars 100,000 light-years wide in what feels like a few centuries, and if you could reach 999,999% of the speed of light, a velocity that is technically possible though engineered beyond our wildest dreams, you could travel to the Andromeda Galaxy, 2.5 million light-years away, in a subjective time of roughly 50 years. In one human lifetime, you could cross the intergalactic void and walk on a planet in a different island universe. The distance has not changed. The galaxy is still millions of light-years away. But for you, the traveler, the distance has contracted. The universe flattens in the direction of your motion, allowing you to step across the abyss as if it were a puddle. This is the loophole. The universe does not forbid interstellar travel. It merely demands speed as the price of admission. It allows you to trade space for time. But what would such a journey look like? What would you see out of the window as you approached the speed of light? The visual experience of relativistic travel would be unlike anything in human history. A psychedelic distortion of reality that would be both terrifying and beautiful. As your spaceship accelerates, the first thing you would notice is the color of the stars. Light behaves like sound. It stretches and compresses depending on your motion. This is the Doppler effect. As you rush toward the stars in front of you, you are slamming into their light waves with increasing frequency. The light waves compress, shifting their color toward the blue end of the spectrum. Yellow stars turn green, then blue, then a violent, piercing violet. Eventually, as you gain more speed, the light from the stars ahead shifts entirely out of the visible spectrum and into the ultraviolet and X-ray bands. To your naked eye, the stars directly in front of you would disappear, replaced by a dark void radiating invisible, deadly energy. Behind you, the opposite happens. You are running away from the light waves emitted by the stars in your wake. The waves stretch out, becoming longer and lazier. The stars turn orange, then a deep blood red. As you accelerate further, they shift into the infrared, then into radio waves, and finally fade into nothingness. The rear window of your spacecraft would look out into absolute crushing darkness, as if the universe you left behind has simply ceased to exist. But the most dramatic effect happens at the edges of your vision. It is a phenomenon called relativistic aberration, also known as the searchlight effect. As you move faster, the photons coming from the sides of the ship appear to be coming from an angle further forward. It is similar to walking through a rainstorm, even if the rain is falling straight down. If you run fast enough, the rain seems to be hitting you in the face. As you approach the speed of light, the entire visual field of the universe begins to warp. The stars that should be to your left and right appear to migrate forward, bunching together in the center of your view. At 99% of the speed of light, almost the entire visible universe is compressed into a small, blindingly bright circle directly ahead of the ship. You are flying down a tunnel of distorted light. The cosmos has warped into a ring of fire, a concentrated beam of radiation that contains the light of millions of stars squeezed into a narrow field of view. Outside of this searchlight, there is only blackness. You are no longer moving through a familiar sky of scattered constellations. You are diving into a singularity of brightness, a geometric distortion where space itself seems to be folding around you. This is the view of a god or a ghost moving through the scaffolding of reality. This visual distortion is a reminder that you are no longer playing by the rules of the slow world. You have entered a realm where simultaneity, the idea that now is the same for everyone, has collapsed. The concept of now on Earth and now on your ship are no longer compatible. You are slicing through space-time at a different angle. This brings us to the profound philosophical weight of the Einstein loophole. It grants us the ability to reach the stars, but it exacts a heavy toll. The faster you go, the more you isolate yourself from the timeline of your origin. When we dream of space travel, we often imagine Star Trek or Star Wars, where ships zip between planets and return home for dinner. Relativity destroys this fantasy. High-speed travel is effectively time travel, but it only goes in one direction forward. If you use the loophole to reach the Andromeda Galaxy in 50 years, you are not just traveling through space, you are traveling through time. When you arrive, 2.5 million years will have passed in the universe at large. The Earth you left will be older by an epoch. The civilization that built your ship will be dust. The language you speak will be a forgotten dialect of a primitive age. This is the bargain of the loophole. Einstein hands us the keys to the universe, but he warns us that we can never truly go home. The traveler becomes an exile, untethered from history, drifting on a raft of slowed time while the river of the universe rages on outside. You can see everything, you can go anywhere, provided you are willing to leave everything you know behind. The speed of light is not a wall, it is a one-way door. However, knowing the loophole exists is one thing. Exploiting it is another. The mathematics of relativity are clean and beautiful on paper. But the engineering required to achieve these speeds is messy, violent, and currently beyond our grasp. To reach the gamma factors that make interstellar travel possible, to reach 99% of the speed of light, we need energy. Not just a lot of energy. We need energy on a scale that mimics the out-h-fout of stars. We need to harness forces that are terrifying in their destructive potential. We need to take the power that destroys cities and channel it into a nozzle. To understand how we might actually build a machine capable of this, we have to look past the gentle ion drives and the passive solar sails. We have to look at the brute force of the atom. We have to look at the dreams of the 1960s, where scientists drew blueprints for ships powered by nuclear bombs. We have to look at the fusion reactions that power the sun and the antimatter that powers the engines of science fiction. The leap from chemical rockets to relativistic starships is not an evolution, it is a revolution. It requires us to master the fundamental forces of nature and bend them to our will. The Einstein loophole is open, waiting for us to step through. But the energy required to take that first step is a fire we are only just learning how to build. The mathematics of relativity offer us a ticket to the stars, a cosmic permission slip signed by Einstein himself, but the universe does not accept credit, it demands payment up front, and the currency it accepts is energy. To achieve the relativistic speeds necessary to dilate time and shrink distance, we cannot rely on the gentle push of ions or the whisper of sunlight. We need violence. We need to harness forces so destructive that they are usually associated with the end of civilization, not its expansion. This realization birthed the most audacious, terrifying, and technologically viable period in propulsion history, the era of atomic dreams. It was a time when humanity, drunk on the newfound power of the nucleus, looked at the atomic bomb and saw not a weapon of war but a stepping stone to the galaxy. In the late 1950s, the world was trembling under the shadow of the Cold War. But in San Diego, At the General Atomics Laboratory, a group of brilliant physicists led by Ted Taylor and the legendary Freeman Dyson were working on something that transcended planetary politics. Their project was code, named Orion. It remains to this day the only technology we have ever conceived that could launch a massive crewed spaceship to the planets and perhaps the nearest stars using 1960s technology. The premise of Project Orion was brutally simple. If you want to move a mountain of steel through space, you do not use a rocket engine. You use nuclear explosions. The design called for a spacecraft of monstrous proportions akin to a trans-oceanic liner standing upright. At its base sat the pusher plate, a massive disc of thick steel coated with graphite oil to prevent ablation. The mechanism of flight was a sequence of controlled catastrophes. The ship would eject a pulse unit, essentially a small, directional nuclear warhead, out through a hole in the pusher plate. The unit would drift a safe distance behind the ship, roughly 200 feet, and then detonate. In the vacuum of space, a nuclear explosion does not create a blast wave of air like it does on Earth. Instead, it creates a shell of superheated plasma, expanding at incredible velocities. This wave of plasma would slam into the pusher plate, delivering a massive kick. Giant shock absorbers, essentially colossal pneumatic springs, would soak up the violence of the impact, converting the sharp jolt into a smooth, sustained acceleration for the crew compartment above. Imagine the launch of such a vessel. It would not be the steady roar of a chemical rocket. It would be a staccato rhythm of thunder, bang, 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 one explosion every second. The ship would ride a pillar of nuclear fire into the sky, leaving a trail of radioactive fallout in its wake. It was dirty, it was dangerous, and it was undeniably effective. Calculations showed that an advanced Orion ship could reach velocities of roughly 3 to 5% of the speed of light. While not yet relativistic, this is fast enough to reach Saturn in months rather than years. It was a spaceship built on the logic of brute force, a way to brute force our way out of the gravity well using the most potent energy source we had ever discovered. But Orion was a dream that died on the drawing board. It was not killed by physics. The physics were sound. Small-scale tests using conventional explosives proved that the pusher plate concept worked. It was killed by the fear of its own fuel. The Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, effectively outlawing the Orion drive. The idea of launching thousands of nuclear bombs into orbit was simply too terrifying for a fragile geopolitical world to accept. Humanity chose safety over the stars. We put the blueprints in a vault and went back to chemical rockets, accepting the slow, safe crawl over the violent, fast leap. Yet for those who dream of interstellar travel, Orion remains a what-if that haunts the imagination, a path not taken that could have put humans on the moons of Jupiter by 1980. If fission, the splitting of atoms, was too dirty for our tastes, the physicists turned their eyes to a cleaner, more powerful fire fusion. This is the engine of the universe, the process that powers the sun and every star in the night sky. In a fusion reaction, light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, are forced together until they merge. The resulting nucleus is slightly lighter than the sum of the original parts, and that missing mass is converted into pure energy. It is the opposite of splitting the atom. It is binding it, and the energy yield is vastly superior. In the 1970s, the British Interplanetary Society launched a theoretical study to see if a fusion-powered starship was possible. They called it Project Daedalus. The resulting design was a Leviathan. Daedalus would be a two-stage spacecraft, weighing 54,000 tons, comparable to a fully loaded aircraft carrier constructed in orbit. It would be powered by inertial confinement fusion. The engine would fire pellets of frozen deuterium and helium-3 into a reaction chamber 250 times a second. Their high-powered electron beams would zap the pellets, compressing them until they ignited in a miniature thermonuclear explosion. A powerful magnetic field, the magnetic nozzle, would then direct the resulting plasma out the back of the ship. The scale of Daedalus was humbling. It was designed to reach Barnard's star nearly 6 light-years away. The ship would accelerate for 4 years continuously, burning through tens of thousands of tons of fuel until it reached 12% of the speed of light. At this speed, it would cross the void to Barnard's star in 50 years. It was a one-way trip for a robotic probe, a grand gesture of exploration that would span a human lifetime. But Daedalus highlighted a critical flaw in all rocket designs, even nuclear ones: the fuel. To reach Barnard's star, the ship had to carry 50,000 tons of fuel. That is 50,000 tons of mass that has to be pushed, accelerated, and managed. And helium-3, the magic ingredient for clean fusion, is incredibly rare on Earth. To fuel a single Daedalus mission, we would need to mine the atmosphere of Jupiter for decades to harvest enough of the isotope. We are trying to bottle a star, but the bottle is heavy, and the gas is hard to find. This problem, the problem of carrying your own propellant, led to one of the most elegant and romantic concepts in the history of astrophysics, the Bussard ramjet. Proposed in 1960 by physicist Robert Bussard, this idea attempts to bypass the rocket equation entirely. Bussard looked at the empty space between stars and realized it wasn't truly empty. The interstellar medium is filled with hydrogen atoms floating in the dark, roughly 1 atom per cubic centimeter. It is a vacuum by terrestrial standards, thinner than the best laboratory vacuum we can create on Earth. But over the vast distances of space, that dust adds up to a lot of potential fuel. Bussard's idea was to build a ship that doesn't carry its own fuel tank. Instead, it harvests fuel as it flies. The ship would deploy a magnetic field of immense proportions, a funnel stretching thousands of kilometers ahead of the vessel. This invisible magnetic web would scoop up the stray hydrogen atoms from the interstellar medium, funneling them into a reactor at the back of the ship. There, the hydrogen would be compressed and fused to generate thrust. It is the cosmic equivalent of a jet engine, which takes in air from the atmosphere to burn fuel. But the ramjet takes in the universe itself. The beauty of the Bussard ramjet is that it has no theoretical top speed limit imposed by fuel mass. Since you are picking up fuel as you go, you never run out. You could accelerate indefinitely. You could keep the engines running at 1g1 Earth gravity of acceleration for years. According to the math of relativity, if you could maintain a 1g acceleration, you could cross the galaxy in a single human lifetime. The ramjet promised the stars without the burden of the tank. It became a staple of science fiction, the golden standard for how humanity would become a galactic civilization. But the universe, as always, is cruel to our dreams. As physicists looked deeper into the mechanics of the ramjet, they discovered a fatal flaw: the drag. To catch enough hydrogen from the incredibly sparse interstellar medium, the magnetic scoop has to be enormous, thousands of miles wide. But when you plow a magnetic field that size through the gas of space, even thin gas, it creates resistance. The hydrogen atoms don't just politely enter the intake, they interact with the field, creating friction. Calculations revealed that as the ship gets faster, the drag from the scoop increases faster than the thrust from the engine. The magnetic funnel essentially acts as a giant parachute. The faster you try to go, the harder the universe holds you back. Instead of accelerating to light speed, the ramjet would hit a terminal velocity, choking on the very fuel it was trying to eat. Furthermore, the hydrogen found in deep space is mostly protons, standard hydrogen 1. Fusing solitary protons is an incredibly slow and difficult process, the same process the sun uses, which takes billions of years. To work in a spaceship engine, we need deuterium or tritium, which are rare isotopes. So the ramjet would have to act as a refinery, sifting through endless cubic light, years of useless protons to find the rare gems of heavy hydrogen, all while fighting the drag of the medium. The elegance of the design collapsed under the weight of particle physics. So we find ourselves in a difficult middle ground. Chemical rockets are too weak. Nuclear fission is too dirty and politically impossible. Fusion is technically possible but requires fuel tanks the size of skyscrapers. And the ramjet, the dream of unlimited fuel, is strangled by friction. We are like a species that has discovered fire but hasn't yet invented the steam engine. We know the energy is there. We can see the stars fusing hydrogen every night. We understand the math that releases the energy. But building a machine that can contain that fire and use it to push us across the dark remains an engineering challenge that dwarfs the construction of the pyramids or the digging of the Panama Canal. Yet, the dream of brute force is not dead. It has merely evolved. Engineers are now looking at hybrid systems. What if we use a fusion drive but we don't carry all the fuel? What if we drop the fuel along the path ahead of time? Or what if we combine the Bussard scoop with a localized fuel supply? The concept of the antimatter catalyzed nuclear pulse propulsion suggests using tiny amounts of antimatter to trigger fusion explosions, shrinking the size of the bombs in the ship. It is a refinement of the Orion idea, still violent, still nuclear, but precise. We are entering an era where we must accept that space travel is not a gentle glide. It is a fight against the inertia of matter. To go to the stars, we must be willing to channel the energies of the apocalypse. We have to be comfortable sitting on top of a controlled thermonuclear detonation. The silence of the void will only be broken by the thunder of our own making. And as we look toward the next horizon of propulsion, we encounter a substance that makes nuclear fusion look like a flickering candle. It is the mirror image of reality, the most volatile and energetic substance in the universe. It is called antimatter, and it promises a fire so pure that it could finally burn away the chains of gravity if it doesn't destroy us first. The ultimate frontier of propulsion does not lie in the brute force of splitting atoms nor in the fusion fires of the sun. It lies in the terrifying symmetry of the universe itself. For every particle of matter that makes up your body, the chair you sit on, and the planet beneath your feet, there exists a shadow twin, a particle of identical mass but opposite electric charge. This is antimatter. It is the rarest, most volatile, and most energy-dense substance in existence. And the moment it touches normal matter, both vanish instantly in a flash of pure gamma radiation. There is no ash, no smoke, no residue. There is only the complete 100% conversion of mass into energy, fulfilling Einstein's equation EMC squared with terrifying literalism. If nuclear fusion is the engine of the stars, antimatter is the engine of creation itself. To understand the scale of this power, we must look at the efficiency of our tools. A chemical rocket like the one that took Apollo to the moon releases energy by rearranging electron bonds, converting roughly 1/1000th of its fuel mass into energy. A nuclear fission bomb, like the one that destroyed Hiroshima, converts about 1/10% of its mass into energy. Fusion, the holy grail we discussed earlier, converts roughly 0.7%. But antimatter is 100%. It is the absolute ceiling of physics. A single gram of antimatter, an amount roughly the size of a paperclip colliding with a gram of normal matter, would release energy equivalent to the atomic bomb dropped on Hiroshima. A spacecraft powered by this reaction would not need mountains of fuel. It would sip from a tank containing just a few kilograms of anti-hydrogen, accelerating to relativistic speeds on a pillar of pure light and hard radiation. The design of an antimatter rocket is a study in magnetic confinement. You cannot hold antimatter in a tank made of steel or titanium or diamond. If the fuel touches the walls of the container, the ship explodes. Instead, the antimatter must be suspended in a vacuum, held in place by powerful magnetic fields, floating in a state of perfect levitation. This device is known as a penning trap. When thrust is needed, the magnetic fields release a microscopic stream of anti-protons into a stream of normal protons. They annihilate, creating a swarm of short-lived particles called pions. These pions move at nearly the speed of light. A magnetic nozzle, an invisible funnel of force, directs these particles out the back of the ship. The exhaust velocity of such an engine would be a significant fraction of the speed of light itself, solving the tyranny of the rocket equation in a single stroke. With an antimatter engine, a journey to Alpha Centauri could be completed in perhaps 10 to 15 years. We could reach the stars within a human decade. But if the physics of antimatter is a dream, the economics are a nightmare. Antimatter does not exist naturally in our universe. We cannot mine it from asteroids or scoop it from the atmosphere of gas giants. It seems that shortly after the Big Bang, for reasons we still do not fully understand, the universe chose matter over antimatter. To get it, we have to make it, and making it is the most inefficient industrial process in human history. We manufacture antimatter atom by atom in particle accelerators like the Large Hadron Collider at CERN in Switzerland. We smash protons together at nearly the speed of light, and in the debris of those collisions we occasionally find a stray anti-proton. We capture it, slow it down, and carefully store it in a magnetic trap. The rate of production is agonizingly slow. If we ran all the particle accelerators on Earth continuously, dedicating them solely to the production of antimatter, it would take roughly 100 billion years to produce a single gram. The cost is equally astronomical. Estimates suggest that a gram of antimatter would cost roughly $62 trillion. To fuel a starship with kilograms of the stuff would require an economy larger than the combined Outhanch-Fout of human history. Furthermore, the storage is perilous. A power failure in the containment magnets, a computer glitch, or a micrometeoroid impact would result not in a mechanical failure but in the immediate conversion of the ship into a new star. We are essentially trying to build a fireplace for a fuel that hates existence. Facing these insurmountable barriers of fuel mass and production cost, some physicists have proposed a radical inversion of the problem. What if the solution to space travel is not to carry more powerful fuel, but to carry no fuel at all? What if we leave the engine at home? This is the concept of beamed energy propulsion, a shift in thinking that transforms the spacecraft from a heavy tanker into a gossamer kite. The idea traces back to the 1960s, but it has found its most mature expression in a project known as Breakthrough Starshot. The premise is to separate the energy source from the vehicle. Instead of a rocket carrying a reactor, we build a massive array of lasers on Earth, or perhaps on the Moon. This array, a light beamer, would combine the Outhanch-Fout of millions of fiber, optic lasers into a single coherent column of light, generating roughly 100 gigawatts of power. That is equivalent to the Outhanch-Fout of 100 nuclear power plants, focused into a beam the width of a few meters. The spacecraft itself would be nothing like the lumbering vessels of science fiction. It would be a star chip, a fully functional space probe shrunk down to the size of a postage stamp, weighing only a few grams. This chip would be attached to a light sail, a mirror incredibly thin, incredibly reflective, and roughly 4 meters wide. The launch would be the most violent event in the history of acceleration. The laser array would fire for just a few minutes. In that brief window, the pressure of the laser light hitting the sail would subject the tiny probe to tens of thousands of Gs of acceleration. It would go from a standstill to 20% of the speed of light, roughly 37,000 miles per second, in less than 10 minutes. At this velocity, the journey to the Alpha Centauri system would take just 20 years. A human lifetime. A scientist could launch a fleet of these starships early in their career and be alive to receive the data when they arrive. The fleet would streak across the void, silent and cold, powered by a push that happened decades ago. As they approached the destination, they would awaken. Cameras, spectrometers, and magnetic sensors would spin up. They would fly through the alien solar system, snapping pictures of Proxima b, the potentially habitable planet orbiting our nearest neighbor. Then they would beam the data back to Earth using a tiny onboard laser. 4 years later, humanity would see the first close-up image of an alien world. The beauty of the light sail is its purity. It bypasses the rocket equation because the fuel stays on Earth. We can build the power plant as big as we want, maintain it, fix it, and use it to launch thousands of probes. It turns interstellar travel into an infrastructure project rather than a survival mission. We could build a highway of light, pushing wave after wave of explorers into the deep dark. But the light sail has a fatal flaw, a tragedy written into its very design. It has no brakes. A spacecraft pushed by a laser from Earth can accelerate brilliantly. But once it reaches its destination, there is no laser at Alpha Centauri to push back and slow it down. The starships would not stop. They would flash through the target system at 1/5 the speed of light, traversing the distance from the planet to its sun in minutes. They would have mere moments to gather data before hurtling out the other side, exiting the system forever into the endless black of the galactic void. They are tourists who cannot stop the car, snapping photos out the window as they scream past the Grand Canyon at supersonic speeds. For a robotic probe, a flyby is acceptable. Better to see for a minute than never to see at all, but for a human crew, this is a non-starter. You cannot launch a colony ship at relativistic speeds if you cannot stop at the New World. To stop a human crewed light sail, you would need a laser array waiting for you at the destination, which requires you to have already gone there to build it. It is a causality loop. Some have proposed hybrid solutions, such as deploying a magnetic parachute or a mag sail to drag against the interstellar medium and slow down. By generating a massive magnetic field, the ship could create friction against the thin hydrogen gas of space, bleeding off velocity over decades. It would be a long, slow deceleration, drifting into the target system like a ship dropping anchor in a storm. But even with these theoretical solutions, we are still dealing with the small scale. We are talking about probes the size of stamps or ships that take decades to slow down. We are still playing in the shallow end of the cosmic pool. To truly unlock the galaxy, to make the distance irrelevant, we need to look at the ultimate limit. What happens if we solve all of this? What if we have infinite energy, perfect shielding, and engines that can push us to 99.999% of the speed of light? What happens when we push the laws of physics until they scream? At this point, we leave the realm of engineering and enter the realm of cosmology. Because even if we build the perfect ship, the universe itself is moving. The ground beneath our feet is shifting. As we look out at the distant galaxies, the targets we yearn to visit, we notice something disturbing. They are turning red. They are fading. The space between us and them is stretching, pulling them away faster than we can build ships to chase them. We are entering the domain of the cosmic horizon, where the ultimate enemy of exploration is not gravity or fuel or time, but the expansion of space itself. The race is not just against our own mortality, it is a race against a universe that is trying to separate us forever. The engineering challenges we have discussed, the crushing weight of fuel, the heat of fusion, the scarcity of antimatter, are merely the local hurdles. They are the problems of a toddler learning to walk. But let us imagine for a moment that we have grown up. Let us assume for the sake of this thought experiment that humanity has solved every technological problem. We have built the perfect ship. It has unlimited energy, perfect shielding, and an engine capable of accelerating us to 99.9999% of the speed of light. We have effectively conquered the laws of motion. We can go anywhere instantly, or so it seems to the travelers on board. At this level of technological godhood, you might assume the entire universe is ours for the taking. You might think we could plant a flag on every galaxy in the Hubble Deep Field. But it is here, at the absolute apex of our capability, that we slam into the final, immovable wall. It is a wall not made of matter, but of space itself. The universe is not a static stage waiting for us to cross it. It is a living, breathing, and stretching entity, and it is growing faster than we can ever hope to travel. To understand the ultimate limit of a human lifetime, we must confront the terrifying nature of the cosmological horizon. We live in an expanding universe. This is not a new idea. Edwin Hubble discovered it in the 1920s. But the nature of this expansion is often misunderstood. It is not that galaxies are flying through space away from us like shrapnel from an explosion. It is that the space between the galaxies is being created. Imagine the universe as a sheet of rubber being stretched. The galaxies are glued to the rubber. They remain stationary relative to their local patch of space, but as the rubber stretches, the distance between them grows. Every second you spend reading this, millions of miles of new emptiness are being silently inserted between us and the distant cosmos. For billions of years, gravity tried to slow this expansion down. But about 5 billion years ago, a mysterious force took over. We call it dark energy. We do not know what it is, but we know what it does. It pushes. It is an anti-gravity of sorts, a vacuum energy that permeates every cubic inch of existence. And unlike gravity, which gets weaker with distance, dark energy is constant. As the universe expands, there is more space, which means there is more dark energy, which causes the universe to expand even faster. This is the horror of the accelerating universe. The cosmos is not just growing, it is running away from us. This acceleration creates a boundary known as the Hubble sphere. Currently, this sphere extends roughly 14 billion light-years from Earth. Inside this sphere, galaxies are receding from us slower than the speed of light. We can theoretically send a signal to them and they can send one back. But outside this sphere, the space is expanding so fast that the galaxies are being carried away faster than the speed of light. This does not violate Einstein's rules because the galaxies are not moving through space faster than light. The space itself is expanding. It is a treadmill that is moving faster than we can run. However, a sufficiently advanced civilization could theoretically catch up to galaxies beyond the Hubble sphere. Since the Hubble sphere is also expanding, a ship moving at near light speed could slowly gain ground. But there is a hard limit, a final line in the sand called the cosmological event horizon. This horizon is currently located about 16 billion light-years away. Any event happening beyond this line, a star exploding, a civilization rising, a signal being sent, will never ever reach us. The light from those events is traveling toward us at 186,000 miles per second. But the space between us is stretching faster than that. The photons are like runners on a track that is lengthening faster than they can sprint. They will run forever, burning out in the void, never reaching Earth. This means that the universe is deleting itself from our view. Every year, galaxies near the edge of the event horizon cross over the line and vanish from our causal reality. They are gone. We can still see their ancient light, the ghosts of how they looked billions of years ago, but we can never touch them, never visit them, and never know their future. The reachable universe is shrinking. If we wait too long, if we hesitate for a few billion years, The local group of galaxies, the Milky Way, Andromeda, and a few dozen dwarfs will be the only things left in the sky. All the other billions of galaxies will have been swept away by the dark flow of expansion, receding beyond the horizon where no ship can ever follow. But let us bring this back to the human scale. What does this mean for our hypothetical traveler on the perfect ship? It means that destination matters. If you aim for a galaxy inside the local group, like Andromeda, the expansion of the universe is overcome by gravity. Andromeda is actually falling toward us. But if you aim for the Virgo cluster, 54 million light-years away, or the Coma cluster, 320 million light-years away, you are in a race against the dark. At 99.9999% of the speed of light, the gamma factor is roughly 707. Time aboard your ship slows to a crawl. You could travel to the Virgo cluster in what feels like just 80,000 years. No. Because of time dilation, that distance of 54 million light-years contracts. For the crew on board, the journey would take roughly 76 years, a single human lifetime. Imagine that. You could board a ship, live a long life reading books and watching the stars warp past your window, and arrive at a cluster of thousands of galaxies that is currently visible only to our deepest telescopes. But here is the catch. While you aged 76 years, the universe outside aged 54 million years. The Earth you left behind has seen mountains rise and fall. The species that built your ship has likely evolved into something unrecognizable or gone extinct. And most importantly, the universe has expanded. The distance you traversed was 54 million light-years when you left. But by the time you arrived, the galaxy cluster has moved. If you try to send a message back home saying, "I have arrived," that radio signal will have to cross a gap that is now much wider. And because the universe is accelerating, there is a possibility that during your journey, your home galaxy has receded so fast that your signal will never make it back. You have not just traveled to a new place. You have traveled to a new epoch, isolated by a gulf of time and space that prohibits any return ticket. Let us push the math to the absolute extreme. Suppose you want to reach the edge of the observable universe, the absolute limit of what we can see today, roughly 46 billion light-years away. You accelerate your ship to a velocity so close to the speed of light that your gamma factor reaches into the billions. You surf the very edge of physics. On board the ship, the journey might feel like 40 or 50 years. You could theoretically reach the edge of the visible cosmos before you die. But what would you find? You would not find the edge. You would find that the edge has moved. The galaxies you saw in your telescope when you left Earth were images from 13 billion years ago. By the time you arrive at their location, billions of years have passed. Those galaxies have aged. The stars that were being born when you left have burned out and died. The civilizations that might have sent the light you saw have risen, fallen, and turned to dust eons ago. And because of the expansion, those galaxies are now vastly farther away than they appeared. You are chasing phantoms. You are running toward a mirage that recedes as you approach. The tragedy of the ultra-relativistic traveler is the tragedy of the Big Rip. As you travel, the universe effectively empties out. Because you are moving so fast, you are fast forwarding the movie of the cosmos. If you looked out the rear window, you would see the universe aging at a hyper-accelerated rate. Stars would flare and die in seconds. Galaxies would spin and dissolve. The background glow of the Big Bang would fade to black. You would arrive at your destination to find a universe that is colder, darker, and lonelier than the one you left. The price of conquering distance is the death of everything you knew. This leads us to a profound realization: the universe has a speed limit not just to prevent us from going too fast, but to preserve the causality of existence. If we could go faster than light, we could outrun the expansion. We could visit galaxies that are currently retreating from us. We could violate the event horizon. But we cannot. We are bound by the speed of light, and therefore we are bound by the horizon. The galaxies beyond that line are not just far away, they are, for all practical purposes, in a different universe. They are causally disconnected from us. No matter how long we live, no matter how fast we build our ships, we can never reach them. So the ultimate answer to how far can we go is a paradox. In terms of subjective experience, there is almost no limit. With enough energy to fuel a high gamma factor, a human could cross the entire observable universe in a lifetime. You could cross billions of light years. But in terms of objective reality, you are limited to the event horizon. You can go as far as the universe allows you to catch up. And every second you hesitate, the horizon shrinks. The universe is slowly closing the door on exploration. The galaxies are leaving. The window of opportunity to be an intergalactic species is vast, but it is finite, and it is closing. We are living in a privileged time in cosmology. We live in an era where we can still see the other galaxies, where the sky is full of structure and light. In the distant future, roughly 100 billion years from now, the expansion will have pushed all other galaxies beyond the horizon. The sky will be empty save for the merged remains of the Milky Way and Andromeda. Future astronomers born in that era will look up and see nothing but endless black. They will conclude that their galaxy is the entire universe, static and alone. They will have no way of knowing about the Big Bang, or the expansion, or the trillions of other worlds that once existed. We are the lucky ones. We can see the exit signs. We just haven't built the car fast enough to reach them before the lights go out. We have spoken of engines that burn with the heat of stars. We have spoken of horizons that retreat faster than light. We have spoken of the mathematics that allow a human being to cheat death and span the galaxy. But we have not yet spoken of the cost. Every equation has two sides, and the equation of interstellar travel is no different. On one side is the miracle of range, the ability to see things no human eye has ever seen. On the other side is the tragedy of loss, the necessity of leaving behind everything that gives a human life meaning. The final limit of how far we can travel is not defined by the fuel in our tanks or the strength of our shields. It is defined by how much of our humanity we are willing to sacrifice on the altar of speed. To understand this sacrifice, we must return to the most famous thought experiment in relativity. A story that physics students learn in their first year but rarely feel in their hearts. It is the story of the twins, Alice and Bob. In the textbooks, it is a dry problem of algebra. In reality, it is a horror story of temporal dislocation. Imagine that Alice is an astronaut, chosen for the first relativistic mission to a star just 20 light years away. Bob is her twin brother, remaining on Earth as mission control. They are the same age, born minutes apart, sharing the same history, the same culture, the same memories. They say goodbye at the launch pad, promising to reunite when Alice returns. Alice's ship accelerates to 90% of the speed of light. On board, the journey to the star takes roughly 10 years. She explores the system for a year, gathering data, taking samples, marveling at the alien sunrise. Then she turns the ship around and accelerates back toward Earth, another 10-year journey. For Alice, 21 years have passed. She left as a young woman of 30. She returns as a seasoned explorer of 51. Her hair has a few streaks of gray. Lines of experience mark her face, but she is still vibrant, still full of life, eager to share her discoveries with her brother. But as her ship decelerates into Earth orbit, the radio silence is the first warning. The frequencies she used to communicate are dead. The navigation beacons have drifted. When she finally establishes contact, the voice that answers is not Bob's. It is not even a voice she recognizes. She lands, and the devastation of the math hits her. At 90% of light speed, while 21 years passed for her, nearly 48 years passed on Earth. Bob, the brother she left in the prime of his life, is now an old man of 78, or perhaps he has already passed away, leaving only a gravestone for her to visit. The world she returned to is half a century removed from the one she left. Fashion has changed, politics have shifted, technology has rendered her knowledge obsolete. She is a stranger in her own home, a relic from the past who stepped out for a moment and missed a lifetime. Now magnify this tragedy. Push the velocity to 99.9% of the speed of light. Send Alice not to a nearby star, but to the galactic center, 26,000 light years away. At this speed, the journey feels manageable to her, perhaps a few decades of ship time. She lives her life in the corridors of the spacecraft, watching the galaxy wheel by. But outside the hull, the universe is aging at a terrifying rate. When she arrives at the black hole in the center of the Milky Way, conducts her research, and returns to Earth, she will not find Bob. She will not find Bob's grandchildren. She will not find the civilization that built her ship. A round trip to the galactic center at high relativistic speeds would take roughly 100 years of the traveler's time. But on Earth, 50,000 years would have passed. 50,000 years. That is the span of time separating us from the Stone Age. When Alice returns, the shapes of the continents will be largely the same, but the climate may have shifted dramatically. Ice ages may have come and gone. The human species might have evolved into something unrecognizable, or merged with machines, or wiped itself out entirely, leaving only ruins reclaimed by the jungle. Alice would land her ship on a silent alien planet that happens to be named Earth. She would be the most lonely entity in existence, a human being with no contemporaries, no culture, no connection to the living world. She would be a ghost haunting the future. This is the fundamental nature of relativistic travel. It is time travel, but it only goes in one direction. Forward. Fast. Irreversibly. Every time you engage the engines of a starship, you are not just moving through space, you are skipping over history. You are fast, forwarding the movie of life on Earth. The further you go and the faster you travel, the more you erase your own past. A traveler who decides to visit the Andromeda Galaxy is making a decision to effectively commit suicide in the timeline of their birth. They will arrive at Andromeda after a journey of 50 subjective years, but 2.5 million years will have passed back home. The human race that launched them will be as distant to them as the Australopithecines are to us. There is no going back. Even if they turn around immediately, another 2.5 million years will pass during the return. They would arrive back on Earth 5 million years after they left. The sun would be slightly brighter. The constellations would be unrecognizable. The concept of humanity might be a forgotten footnote in the geological record. This reality forces us to redefine what we mean by exploration. Throughout human history, explorers Magellan, Columbus, Cook, Armstrong always operated with the assumption of return. They ventured into the unknown, but they remained tethered to the timeline of their culture. They could bring back gold or spices or moon rocks and place them in the hands of the king or the president who sent them. There was a continuity of experience. Relativistic space travel severs this tether. It cuts the cord of causality. The explorer becomes an exile. The data they collect, the wonders they see, the life they discover, none of it can be shared with the people who matter to them. They can transmit the data back via radio, but the signal will take millions of years to arrive. By the time the message I made it reaches Earth, the civilization that needed to hear it will have turned to dust. The solitude of the relativistic traveler is absolute. It is a solitude deeper than that of a hermit in a cave or a sailor adrift at sea. It is a temporal solitude. Imagine looking out the window of your ship at the Earth receding behind you. You are not just seeing the planet get smaller, you are watching it age and die. You are watching your loved ones wither, your cities crumble, your mountains erode, all in the span of a quiet afternoon on the flight deck. You are God, like in your longevity relative to them, but powerless to interact. You are trapped in a bubble of slowed time, preserved in amber while the world burns. And yet, there will be those who choose to go. The drive to see what lies over the horizon is encoded in our DNA, deeper than the fear of loneliness. There will be people who look at the trade, off a billion light years of range in exchange for everyone they ever knew, and say, yes. These will be the ultimate nomads, the pilgrims of the void. They will form a new kind of civilization, a society of travelers who live between the stars, meeting only rarely, existing in a timeline separate from the planets they visit. To them, planets will be fleeting, ephemeral things, blinking in and out of existence like fireflies, while they, the travelers, endure in the slow, stretched time of the high-velocity trajectory. We must also consider the destination itself. If you travel far enough to the galaxies that we can barely see today, you are not just visiting a new place, you are visiting a different era of the universe. Because of the expansion we discussed, the universe is becoming colder and darker. A traveler who spends a subjective lifetime crossing to a distant supercluster might arrive to find that the stars there have begun to burn out. They might find a universe in its twilight. The exploration of the cosmos is a race against entropy. We are trying to see the show before the theater closes and the lights go out forever. So how far can a human travel in one lifetime? The answer is not a number. It is a question of values. Physically, the limit is the edge of the observable universe. You can go anywhere that light has not yet outrun. You can span billions of light years. But emotionally, the limit is much closer. The limit is defined by the endurance of the human heart. How far can you go before the weight of isolation crushes you? How far can you go before the knowledge that you are the last of your kind becomes unbearable? Perhaps the ultimate journey is not about distance at all. Perhaps it is about perspective. When we look up at the night sky, we are looking into a mirror. The vastness of the empty space reflects the fragility of our own existence. The silence of the void amplifies the value of the noise we make here on Earth, the music, the laughter, the arguments, the breathing. The fact that we are trapped here in this tiny pocket of space-time, bound by the speed of light, might be the very thing that makes our lives matter. We are forced to live together, in the same time, in the same moment. The walls of the prison are also the walls of the home. As we drift through the cosmos on this pale blue dot, moving at a humble speed around a humble star, we should remember that speed is not the only metric of success. The Parker Solar Probe is screaming at 430,000 miles per hour, but it is alone. Voyager is drifting into the dark, carrying a golden record that no one may ever hear. We are slow, we are small, we are short-lived, but we are here. And we are together. In a universe of infinite distances and accelerating horizons, connection is the rarest phenomenon of all. The journey to the edge of reality is open to us. The physics are waiting. The engines can be built. The antimatter can be harvested. But before we light the fires that will carry us away from the sun forever, we must ask ourselves not just if we can go, but if we should. For in the end, the greatest distance a human being can cross is not measured in light years, but in the space between two people who understand each other. And that is a journey you can take without ever leaving the ground. If you have drifted with us this far through the gravity wells and the time dilations, through the atomic fire and the cold expansion, thank you. The universe is vast, and exploring it is better with company. If you found comfort in the dark, or wonder in the void, consider joining our community of night travelers. Subscribe to keep the signal strong and let us know in the comments if you had a ticket to the Andromeda Galaxy. Knowing you could never return to the Earth you know, would you take it, or would you choose to stay? Until the next journey, look up and sleep well.